Authorship classification, recognizing writing styles. In this lesson, we solve the problem of identifying an author based on the style of writing in a text. This matters in areas like digital humanities, authorship analysis, and literary research. The learner will learn to load, explore, visualize, and build a machine learning model to classify texts by author. Explanations focus on intermediate beginners getting comfortable with real-world data and predictive modeling. You will also practice error handling and best practices for working with classification data. Running the cell now. We import NumPy for working with numbers. We import pandas to handle tabular data like data frames. Matplotlib lets us plot figures and graphs. Seaborn provides easier and more beautiful visualizations. We use train_test_split to create training and testing sets for model evaluation. Standard scalar scales features so they are on similar ranges, which helps models perform better. Logistic regression is a good starter classification model for multi-class problems like ours. Classification_report, confusion_matrix, and accuracy_score help us understand model performance objectively. Warnings lets us control unnecessary warning messages we may see. We set warning filters so unwanted warnings will not distract us. We set the random seed to 42 for reproducibility so our work stays consistent. Running the cell now. To reinforce, try removing or commenting out one import. What happens? Subscribe for more clear, hands-on tutorials on YouTube. Understanding the data and its structure. The dataset comes from OpenML and is named analCatData_authorship. Our data represents stylometric features from various literary works, labeled by author. There are 841 rows, samples, 70 numeric features, and 4 target classes: Austen, London, Shakespeare, and Milton. Each row contains numbers, such as word frequencies or other style markers, not raw text. Common mistakes: assuming features are words, ignoring class imbalance, forgetting to check for missing data, or treating target as numbers instead of categories. Running the cell now. We import fetch_optimal to load the dataset directly. We download the dataset by its OpenML data ID, loading it as a pandas data frame. We extract the data frame part of the dataset to make it easy to work with. Showing the shape gives us the number of rows and columns. Here we display the first few rows to preview what the data looks like. Running the cell now. The output confirms the dataset has 841 samples and 71 columns, including 70 numeric stylometric features plus the target columns, book IDs, and author. The preview shows word frequency counts per sample and the corresponding author labels, highlighting how the data quantifies writing style rather than raw text, key for building author classification models. Practice: try printing df.columns to see all available features. Let us print out all the feature names to get a sense of what is available. We now show the proportion of each author in the data so we understand class balance. Here we print the normalized frequency of each author label. Running the cell now. Here, we first confirm that our dataset contains many numeric features representing word frequencies plus metadata like book ID and the target author. Notably, the class distribution shows Austen and London dominate the samples, while Milton is the least represented, highlighting potential class imbalance to consider in analysis or modeling. This understanding sets the foundation for how feature columns relate to authorship labels in stylometric classification. Question: is this a balanced problem or is one author much less frequent? Try finding which is least represented. Beginner example 1, simple feature descriptions. Let us look at a few features and basic statistical summaries. Understanding the scale, minute, max, and spread of the numbers is key. Even though there are 70 features, we focus on the first 5 to keep it simple. Running the cell now. We use .describe to print summary statistics for the first 5 columns. Running the cell now. Here, the .describe output summarizes key statistics for the first 5 features, showing their counts, means, and value ranges. Notice that all features have the same number of observations, 841, and the means and spreads vary widely, revealing different usage frequencies. This helps us understand the scale and variability of these features before further analysis. Practice. Try .describe.t to see transposed results for better readability. Checking for missing values is important. We add them up across the entire data frame. Running the cell now. Here, we check for missing values in the entire dataset and see that there are none, which means our data is complete and ready for analysis. This step is important because missing values can affect the accuracy of our feature descriptions and any models we build. Ensuring no gaps lets us confidently explore the scale and distribution of the first 5 features next. In practice, try setting a value manually to NaN and rerunning this check. Beginner example 2, data visualization. Basic data plots help us see distributions and class balance. We will use Seaborn and Matplotlib for easy visualization. Running the cell now. This plot shows us how many samples there are for each author label. We add a title to describe the plot. We display the plot on screen. Running the cell now. This count plot shows the distribution of data points across different authors, helping us quickly identify which authors have more or fewer entries in the dataset. Notice the varying bar heights, which indicate class balance or imbalance, key for understanding potential biases before modeling. This visualization aligns with our lesson goal of using basic plots to explore and summarize categorical data effectively. Extension. Try plotting for one of the feature columns instead of author. Beginner example 3, splitting data for training. Machine learning requires separating the data into training and test sets. We make sure to split in a reproducible way and stratify by author to preserve balance. Running the cell now. We separate out our target column from the data features. Y holds the author labels we want to predict. We split into training and test sets, keeping class balance and reproducibility with random_state equals 42. We print the shape of our training data. We print the shape of our test data. Running the cell now. Here we see that the training set contains 672 samples and the test set has 169, both with 70 features each. This confirms our 80/20 split while preserving feature dimensions. Splitting like this ensures our model trains on most data but is evaluated fairly on unseen data. Try changing test_size to 0.3 and rerun to see what changes in the output. Intermediate example 1, feature scaling. Features may have very different numeric ranges that confuse models. We standardize to mean equals 0 and std equals 1 with standard scalar, fitting only on train and applying to test. Running the cell now. We set up a standard scalar for normalization. We fit on training data and transform it to scaled values. We transform test data by applying the same scalar. We show that after scaling, feature means are close to 0 for the first few columns. We also show the standard deviations are close to 1 for the first few columns. Running the cell now. The output shows the means and standard deviations of the first 3 features in the scaled training set, confirming they are very close to 0 and exactly 1, respectively. This verifies that the standard scalar successfully standardized the features to have mean equals 0 and std equals 1, which helps models train more effectively despite differing original feature scales. Note that scaling is fit only on the trained data to prevent data leakage. Always fit the scalar on the training set, not the test set. Why do you think that is? Intermediate example 2, training a simple classifier. Logistic regression is a good starter multiclass model. You will see how to fit, predict, and check accuracy. Running the cell now. We set up a logistic regression model, allowing extra iterations for convergence and reproducibility. We fit our model to the training set. Now we make predictions on the test set. We measure how many predictions were correct with accuracy_score. Running the cell now. Here, the logistic regression model has been trained on scaled training data and tested on unseen data, achieving a high accuracy of about 99.4%. This demonstrates the model's strong performance in correctly classifying the test set, highlighting that logistic regression can be an effective baseline classifier for multi-class tasks. The code's intent was to fit, predict, and evaluate accuracy, which this output confirms successfully. Practice: try changing max_it to 50 and watch for warnings or changes. This provides precision, recall, and F1 score per author class. Running the cell now. This classification report shows near-perfect precision, recall, and F1 scores across all author categories, indicating our logistic regression model is highly accurate in distinguishing between them. Notice the high support counts, especially for Austin and London, which reflect a solid sample size for those classes. This output confirms the model's strong performance and demonstrates how to effectively evaluate multi-class classification results. Which author is hardest to classify? Why do you think that is? We create a confusion matrix of actual vs predicted authors. This plot makes it clear where misclassifications happen. We label rows as true classes. We label columns as predicted classes. This gives the plot a title for clarity. Display the matrix. Running the cell now. This confusion matrix shows how well the logistic regression classifier predicted each class by comparing the true labels, rows, to the predicted labels, columns. Notice the diagonal values are highest, indicating many correct predictions, which reflects the model's accuracy. This visual summary helps assess the classifier's performance and highlights any classes that may be confused more often. Challenge: what type of mistake is worst for you in your application, confusing Austen and London, or Milton and Shakespeare? Intermediate Example 3, Exploring Feature Importance. Logistic regression gives us model coefficients for each feature, which can indicate importance. We will extract the top 5 coefficients for each author label. Running the cell now. We store the feature names for labeling. Loop through model coefficient rows for each class label. Get the coefficients for this class. Find indexes of the 5 largest coefficients by magnitude. Print a header for each author. Print each top feature and its coefficient. Running the cell now. This output lists the top 5 most influential features for each author, based on the absolute values of the logistic regression coefficients. Notice how each author has a unique set of words with strong positive or negative coefficients, highlighting which terms most distinguish their writing style. This connects to the lesson's goal of interpreting model coefficients as feature importance to better understand what drives classification decisions. Try: how do top features for Austen compare to Milton? Are there patterns? Advanced Example 1, Cross-validation for model reliability. To better estimate generalization, we use cross-validation. Let us score our logistic regression model with 5-fold cross-validation. Running the cell now. We import cross_val_score to automate cross-validation scoring. Score our classifier using 5 training folds for better performance estimate. Display the fold-by-fold accuracy scores. Show the average and spread of estimated accuracy. Running the cell now. The output shows the accuracy scores for each of the 5 folds in the cross-validation, with values very close to 1, indicating consistently high model performance across different data splits. The mean accuracy near 0.999 and the low standard deviation confirm that the logistic regression model is both accurate and reliable. This reinforces the lesson's point that cross-validation provides a robust estimate of how well the model generalizes to unseen data. Try CV equals 10 or scoring equals F1_ weighted for more practice. Advanced Example 2, Visualizing high-dimensional data. With 70 features, it is useful to reduce dimensions for visualization. We will use PCA to project the data onto 2 axes and color points by author. Running the cell now. We import PCA for dimensionality reduction. We set up PCA to project to 2 dimensions and fix randomness. We fit PCA to the training data and get the new representation. Open a bigger plotting window for clarity. Scatterplot the new 2D data, coloring by author class. Add a plot title so readers know what they are seeing. Label the x-axis as PCA1. Label the y-axis as PCA2. Show the legend for author names. Display the final plot. Running the cell now. This scatterplot shows the training data projected onto 2 principal components, effectively summarizing the original 70 features into 2 dimensions. Notice how the points cluster by author, indicating that PCA captures meaningful variation related to authorship. This visualization confirms that dimensionality reduction can reveal underlying structure while enabling clear, interpretable plots. What do you notice about the clusters? Are all authors easily separated? Error handling and debugging examples. It is vital to detect and handle issues gracefully. Beginners often forget to check for non-numeric values or bad input during scaling or prediction. Let us create an artificial error to see what happens. Running the cell now. Explain that we are intentionally inserting a string into a numeric feature to create an error. Create a copy of the training data to preserve the original dataset. Insert the string hoops into the first cell of the copied data to simulate corrupted data. Start a try block to attempt scaling the corrupted data and catch errors. Attempt to fit and transform the scaler on the corrupted data, which should cause an error. Catch any exceptions raised during scaling and print the error message. Running the cell now. This output shows a clear error message triggered by inserting a non-numeric string into a numeric feature column during scaling. Notice the could not convert string to float message, which highlights the importance of validating data types before scaling. This example reinforces the lesson's intent to anticipate and gracefully handle such data issues to prevent crashes. Best practice: always make sure your data is completely numeric before scaling or learning. Intentionally try to predict with the wrong number of features. We expect a value error because input dimensions are wrong. Print error and see what the message tells us. Running the cell now. This output shows an error message indicating a mismatch in input shape. The model expects 70 features, but only 3 were provided. This highlights the importance of validating input dimensions before prediction, reinforcing the lesson on detecting and handling errors gracefully to avoid crashes during model use. When errors appear, read the error message carefully before searching for solutions. Best practices and common patterns. Always separate train and test data before scaling or modeling. Check class balance and consider balancing if needed. Use cross-validation to get robust estimates. Start with simple models and add complexity only as needed. Read every error message, do not ignore warnings. Running the cell now. This code shows how to compute class weights for imbalanced datasets. We import a helper from Sklern for class balancing. Compute class weights automatically from our data. We print the computed weights for each class label. Running the cell now. This output shows the computed class weights for each author in the training set, revealing that Milton is significantly underrepresented compared to others. These weights help the model compensate for this imbalance by assigning more importance to minority classes during training. This step aligns with best practices to handle class imbalance before modeling, improving fairness and performance. Try, how could you use class_weight in logistic regression? End-to-end example, save and visualize final predictions. Let us make predictions on our test set and save the results. We will output a CSV with each text's true author and model prediction. This is useful for post-model analysis or submission. Running the cell now. Build a new data frame showing the actual and predicted authors for each test sample. Save these results to a CSV file for later review. Print the first 5 rows to preview the saved predictions. Running the cell now. Here we see the first 5 rows of our results data frame, showing both the true authors and our model's predictions. Notice that for these examples, the predicted authors match the true authors, indicating correct predictions. This confirms that our code successfully saved aligned results, which is important for further analysis or sharing. Let us open and inspect the predictions file we just saved. Open the CSV to examine the output with your own eyes. Recap and next steps. Today you went from raw authorship data to an evaluated, interpretable classification model. We covered data cleaning, scaling, modeling, interpretation, saving outputs, and error handling. Remember to like and subscribe for more practical data science lessons. Ready to try your own dataset? Tweak features, models, or add more error handling for a real challenge. Running the cell now.